Okay, welcome everyone to today's seminar, PCS-IBS seminar. It's a great pleasure, and today it's something new. So our today's speaker, Kyungmin Lee, is actually at our center at the moment. So he will be presenting this seminar from the seminar room where limited number of people can enjoy a seminar in kind of the old way. Yes, so our today's scientific host is Munjib. So Munjib, please introduce our speaker and let's start the seminar.
Can you hear us or?
Yes, yes, I can hear you.
Okay, so I will introduce today's speaker. So today's speaker is Dr. Kyungmin Lee from National High Magnetic Field Laboratory in Florida State University. So he graduated from Seoul National University and got PhD in Cornell University from Professor Euna Kim. So he has done variety of physics research, including topological materials, non-equilibrium physics, and quantum magnetism. So I think he's one of the most brilliant doctors that I know. So today he's gonna talk about a thermal behaviors in frustrated system, Hilbert space fragmentation, and quantum scarce. So Mike is yours.
Thank you, Dr. Park. I want to thank you for organizing this seminar on such a short notice. So today I'm going to tell you about athermal behaviors in frustrated systems. It's going to be based on these two papers, mostly focusing on the second paper here at the bottom, which has been posted on arXiv and just been accepted for publication. So let me start with acknowledging my collaborators. This work has been done in collaboration with Ron Melendrez, Hitesh Changlani at Florida State and National High Magnetic Field Laboratory, and Arjit Pal at University College London. So broadly speaking, today's presentation touches upon the topics of great recent interest, which is the non-equilibrium dynamics in isolated quantum systems. So thanks to experimental advancements, there has been a lot of progress in realizing isolated quantum systems. They're not only useful as ingredients for quantum computers, they also provide ground for us to study interesting questions of fundamental quantum physics, such as thermalization and chaos. So if you have a system taken out of equilibrium, now over time, it will relax back to thermal equilibrium. Now, this is believed to be the case also for isolated quantum systems, where if you measure observable for long enough time, it'll converge to the expectation value given by this Boltzmann factor. But at the same time, we know that from Schrödinger's equation, that isolated quantum systems undergo unitary time evolution, which is a reversible process. Especially the eigenstates of the Hamiltonian will remain stationary, only their phases will change. So how do you reconcile the two? On the one hand, you have relaxation to an equilibrium state. On the other, you have a reversible process, so the system perfectly remembers where it came from. And eigenstate thermalization.
Excuse me, can I ask a question? Do you hear me? Yeah. Right. The same can be said also about many classical systems which enjoy time reversal evolution, and yet which also thermalize, or
That's right.
not maybe. So what's the special point here about quantum or unitary then?
Well, yeah, so you can say similar thing for classical systems, and there the solution is through chaos and this randomness in motion. There's a quantum version of that, which is the eigenstate thermalization hypothesis. So essentially, what ETH says is that all eigenstates of a generic many-body Hamiltonian with finite energy density are thermal. And by thermal, I mean that if you measure a local observable, and the emphasis is on the local, if you measure the local observable for any eigenstate, then it should equal the expectation value given by the microcanonical ensemble of the corresponding energy with some fluctuation.
Sorry, question again. What means local?
Local means that it's limited to some small region in the real space.
Yeah, but what means real space then?
What means real space?
Now, yeah,
so
because
in the same sense that yes.
Because it seems at the first glance that things depend on the basis simply, which I choose on my Hilbert space basis.
But there's always a sense of real space, like position-wise, right?
No.
Well,
if I'm from Mars, I don't understand what it is meaning. What I mean. So what means real space or local?
Okay. You're asking about mathematical definition of what is real space? Not
really mathematical, but at least some intuition what you might mean by that.
In the same sense that, like if you consider Hamiltonian, right? There's, we can maybe sharply, but we can roughly define what is local Hamiltonian, what is not local, right? Like for instance, if the interaction between particles decay with exponential, then we know that it's local in real space.
Oh. I'm still guessing around. I guess the guy from Mars is still guessing around. Maybe not. Maybe it's just me. Yeah, I understand. If you talk about interactions, you can talk about short-range interactions in that space, in that Hilbert space choice where these interactions are short-range. You could talk about locality. But you didn't tell me what interaction means here, because you just say you have some interacting many-body or whatever Hamilton quantum system. So
okay.
But maybe we can postpone this to a later discussion.
Sure. Okay.
Thank you.
Right. So if you measure, let's say, I mean, we can discuss what it means to be local, but let's say we have a definition of a local, and then we measure some local observable, right? It could be magnetization or some density of charge or something that's confined to a small region in the real space. Then it should equal the microcanonical ensemble, the expectation value given by the microcanonical ensemble. And a slightly different way to formulate this is using density matrices. So if the above statement is true, that all the local observable that you measure equals that of the thermal ensemble, then if you consider a subspace of the whole system and then look at the reduced density matrix, now that should equal the reduced density matrix given by the thermal ensemble. And an interesting and very important corollary of this is that if you consider the entanglement entropy of any eigenstate with finite energy density, that should equal the thermodynamic entropy, which follows a volume law. So what this tells us, what ETH tells us, is that if you have eigenstate with finite energy density, then different parts of the system are strongly entangled with each other, so that the system acts as its own heat bath. Okay, there are cases where ETH is violated. The most well-known classes of systems that violate ETH are the integral systems, which are exactly solved by Bethe ansatz, and disordered systems, the many-body localized systems where strong disorder prevents the system from thermalization. So in both of these cases, the system retains memory of its initial state through extensive conservation laws. Yes?
Yeah, so what about frustrated systems? I'm basically thinking, I think now there are definitely examples where you don't have disorder, but I'm not sure the systems are integrable in the sense that they're solvable, and yet they fall under this category.
So I will talk about the frustrated systems in the next slide. Right, so these two examples, if you think about these two examples, then you have athermal behavior that's coming from the system being trapped in some part of the phase space. So this brings in this notion of fragmentation of Hilbert space, where if the Hilbert space is broken up into little pieces, and you're stuck in one of the fragments, then you cannot travel to other fragments. And you lose thermalization in that case. So in this talk, I will talk about how frustrated systems can give rise to such strange behaviors, such athermal behaviors, without having to rely on disorder. And if I have time, I will also mention how quantum scars arise in these frustrated systems. Yes.
Yeah. So loudly. Okay. Yeah. I mean, I know very well that when you have quantum scars, you have fragmentation. This is a one-to-one thing. But I didn't know that, for example, in MBL case, you also have the fragmentation of the Hilbert space. Is that the case?
Yeah. So in MBL, you have local integrals of motion, right? And which are you have local integrals of motion where you can essentially describe the system as Ising variables, and these are weakly connected, and that's how you get how you lose. The difference is that in quantum scars, fragmentation is not associated with C. Right. So quantum scars is a special case where the rest of the Hilbert space is well connected. It's just a few states or measure zero states are disconnected, and these are behaving in a strange way. Yeah. Okay. Yes.
Basically a follow-up to Darius' question. So are there any conservation laws associated to quantum scars, or even?
Yeah, that's a good question. I think it's at a very early stage of research in quantum scars, and people do talk about, let's say, some quasi-symmetry, or some people call it quasi-symmetry, where you don't have the symmetry of the whole Hilbert space, but if you limit to some scar state, like subspace spanned by the scar states, then sometimes you have these emergent symmetries. Yes. Right. Right. It also depends on what really is a scar, right? I think in many of the examples that people have found, that it is the case, and that also has to do with this perfect revival of the states. I mean, if you think about quantum scars as some states with weak entanglement, then it's not really a necessary condition. So it really depends on what you define as scars, and I don't think I think people in the community are still trying to define what really is a scar.
Sorry to interrupt, but can we get another mic, because the people from listening via Zoom can only hear what is said on the microphone. So when you discuss, we cannot hear. Yeah. Okay, thank you.
Actually, I think that in quantum, I mean, the fragmentation that we are talking about in quantum scars is not a fragmentation that separate the scars from the rest of the spectrum. We are already in a room, so we are already in a fragment, and that fragment presents this fragmentation. So it's better to clarify. I mean, the fragmentation happens at a different stage, not at the stage of, okay, yeah.
Okay, any other questions or comments? If not, I will continue. So frustration is, what is frustration, right? Frustration is when you have competing interactions so that the system does not know how to order. As shown in this example of an antiferromagnetic triangle, there's no way to satisfy all the three bonds, so the system not decide what's the, I mean, there are multiple ground states in this case. And there are various frustrated lattices in 1, 2, and higher dimensions. And in this talk, I will focus on the Kagome lattice in particular. And one of the hallmarks of a frustrated system is the residual entropy. Because the system does not know how to order down to very low temperature, you have a remaining entropy in the system, and still system is still exploring the phase space. And this is going to be a very important property that we will make use of in constructing these athermal behaviors. So as I said, I will focus on the Kagome lattice, and Heisenberg antiferromagnet on a Kagome lattice has been studied extensively in the context of searching for a quantum spin liquid ground state. However, after decades of study, like many theory works, it's still being debated what the true ground state of this Hamiltonian is, whether it really even is a quantum spin liquid. But I'm not going to be focusing on the ground state. I'll be looking at excited spectrum and their properties. One of the things that's been very well known in the community is that the Kagome antiferromagnet has many low-lying singlets, and there was theory work that have suggested that maybe these singlets violate EPH. And there were also theory works that suggest Bragton excitation can be possible in Kagome lattice, and also in classical models, spin freezing has been observed in theory. So instead of focusing on the Heisenberg model, I will introduce another knob to tune and study the XXZ Hamiltonian. So where I allow the Z interaction to be different from the XY interaction. And this model has a very interesting point at Jz equals to -12. So J perp is set to 1, antiferromagnetic. But if you go to Jz equals to -12, then you have exponentially large ground state degeneracy. And these ground states can be found quasi-exactly. And let me explain what I mean. So because this Hamiltonian is a two-body Hamiltonian, consists of interactions between bonds, interactions that live on the bonds, you can now group the bonds into triangles. And if you look at a single triangle now, because all the three spins are connected to each other, you can write the Hamiltonian on a single triangle as a function of the total spin. And if you look at the spectrum of a single triangle, at the Heisenberg point, you have two degenerate manifolds with dimension 2 each. But if you go to this threshold point, which I call the mother point, then it again has two degenerate manifolds, but the upper manifold has dimension 2. And the states that comprises this upper manifold can be written in this way. And you can think of this as zero angular momentum Magnon states, if you will. Now you can write the Hamiltonian at this point. You can write the Hamiltonian as a projector to the upper manifold. So any state that gets projected out by these two states live in the lower manifold, and it's a ground state of a single Hamiltonian. I mean, ground state of a single triangle. And now you can convince yourself that if you have in-plane spin configurations that are 120 degrees to each other, then you're in the ground state. So if you take, let's say, tensor product of these three spin coherent states, you get terms like up, 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 which is not included in here because it's SZ equals to 3/2. So you need to be in the S equals to plus or minus half. Now, if you look at such a component, let's say you look at up, up, and then down, up, and up, down. That's in the S equals to plus half sector, but it comes with phase factors of 1 omega and omega squared. So you're orthogonal to these two states. And now you can extend this idea to the whole lattice, where as long as you have 120 degrees configuration on every triangle, you're guaranteed to be in the ground state. So this And using this property, this finding the ground state of this Hamiltonian becomes finding 3 colorings of this Kagome lattice, where the 3 colors represent 3 different spin configurations. Here are 2 examples of such colorings. On the left is what is often called the Q equal to 0 state because of its translation invariance. On the right is what is often called the √3 by √3 state because of its ordering wave vector. These are 2 different magnetically ordered states, which are both of which are eigenstates, and okay, they're ground states of this Hamiltonian at the mother point. And these are product states at the same time. Yes.
What is the general rule that this coloring problem should satisfy to be the ground state?
Right, I will get there. So there are actually not just these 2, but exponentially large number of colorings on the Kagome lattice, which scales as this number to the power of n. And so this defines, this exponentially many states define a submanifold of the Hilbert space with some local constraint. The local constraint is that if you have 2 sites that share a bond, then they should be of different color. So you have 3 colors to choose from, and whenever there's a bond between 2 sites, they should be of different colors. And as long as you satisfy that, you know that you're in the ground state of this Hamiltonian. Okay, so this coloring construction can be applied not just to Kagome lattice, but also to other lattices in 1D and higher dimensions, as long as you have triangular motifs. And there's also a version of this where you can generalize this to other motifs like square and so on, but the Hamiltonian starts becoming less physical. Yes?
Maybe I should go there. It's easier. No. So just wondering, this coloring that you do, is it always possible to do it in the thermodynamic limit, or will you reach some large finite sizes like quasicrystals where you'll no longer be able to do coloring beyond that?
I mean, whether it's possible to do the coloring. Yes, you can always do this. For any lattice with triangular motifs at that special point, right? Yeah, I mean, it doesn't depend on whether coloring is possible. Doesn't depend on whether it's a finite size or not. You can always. Okay, so yeah, coloring construction is.
So maybe I'm jumping ahead, but so you're mentioning that degeneracy might be exponential or not. So can you give an example of a non-exponential one?
Yes. Yeah, I was just about to get to that. So if you consider triangular lattice, let's say you want to color the triangular lattice with 3 colors. You pick a let's do it, right? So you pick a color here. You can choose 3. You have 3 colors to choose from. Let's say you pick green. This can be red, or this site can be red or blue, right? Now let's pick blue. Then this has to be red, and this has to be green, and so on. So every site, the rest of the sites is fixed, right? Once you choose few sites. So there's only finite number of colorings possible on triangular lattice, whereas on the Kagome lattice, there's less connectivity in some ways, so that there's exponentially large number of degeneracy. Yes. So if you have, in general, if you have corner sharing triangles, then you tend to have large degeneracy. Whereas if you have edge sharing, then it's much more constrained, and you don't get nice lattice. Yeah. Oh, okay.
We cannot hear the question. Sorry.
Okay, the question was about dice lattice, but I'll need to think about it. I don't know the answer on top of my head. Okay, so and one of the interesting things that I want to point out is that these coloring states are not all related by symmetry operations. for example, this Q equal to 0 state and root 3 by root 3 state are not related to each other by translation or rotation. And one way to see this is through what is called the Kempe loops. So these are loop excitations in these coloring states. So what are these Kempe loops? These are nothing but two color loops. So here I'm showing you one color loop in the Q equal to 0 state, two color loop in the Q equal to 0 state, where I pick the green, red, green, red, green, red. So I follow green, red, green, red, green, red. And that forms, in a periodic boundary condition on a torus, it always forms a loop. Whereas if you have open boundary condition, it can end on the boundary. And that always winds around the system in the Q equal to 0 case. It always goes straight. Whereas for the root 3 by root 3 state, you have two colored loops that wind around hexagons. So here, this green-red loop winds around this hexagon. And if you consider this blue-green loop, let's say, that one also winds around hexagons. So there's no way to map this topological loop to a local loop. And because these loops have different lengths, now this introduces some length scale to the states and the three coloring states. And one way to make use of these loops to connect different states is through the Kempe move, which is I pick a Kempe loop, and then I exchange the two colors within that loop. So for example, if I pick this loop, I can exchange the green to red, red to green, red, green, red, green. Now that's a new coloring. It's a different coloring from the original one, but it's still valid because within the loop, you always satisfy the constraint. And the neighboring sites are always blue. So you're guaranteed to be in the coloring manifold. If you start from the coloring manifold state in the coloring manifold, you always end up in another state in the coloring manifold. And this gives us a way to connect different colorings. And you can think about the simplest Hamiltonian that makes use of these loops, where yes.
When I do this, what is the name, Kemp move, should I do for a specific loop or for all the loops parallel? For example, I mean, here I have this loop and I have all the parallels. This swap of the colors can be done for a single loop, right? I shouldn't do, I mean, I don't have to do for all the parallel loops, right? Okay.
Yeah, and a simple question. So these Kempe loops, are they related to the, say what you have in pyrochlore-like lattices? There you have the ground state that can be mapped onto like 2 in 2 out rule, and then you can also explore the configurations by doing loops. Well, you simply flip the spin, which violates the 2 in 2 out constraint, then you flip another spin and you do so until you close the loop. So is it similar or construction or not exactly?
I mean, you could say it's similar because in both cases you have these loop that always, make sure that you're in the ground state manifold, right? But I mean, it's a very different model, so I don't know how far the right.
We couldn't hear the comments. Is it possible to get 2 mics? Our technical
we only have
support.
1 mic, right? So
Okay.
I'm very sorry.
Yes,
So
then
asking,
please, if you can
we'll try
it.
to speak with that.
Okay.
Yes, I was asking whether all colorings are connected by Kempe moves, but that's just on the next slide. And so I was saying that this 2 in 2 out loops, I think there's at least in some models, there's a proof that you can explore the entire manifold.
Right. I think for the ice manifold, the situation is somewhat similar to the quantum dimer model, where you have topological sectors, but within the sector, all the states are connected. I'll show you what the answer is for this in the next slide. Okay. So, right. So you can write some Hamiltonian. The simplest version of the Hamiltonian would be just to introduce tunneling between 2 states that are connected by a single Kempe loop. And and of course the coefficient is more important. You can assume that, okay, the coefficient depends on the length of the loop, because the longer the loop, the more spins you need to flip. So the less likely the tunneling would be. And this Hamiltonian connects length scales of the states to some relaxation time scale. You can ask the question there was just this question, whether the time evolution with this Hamiltonian is ergodic, or in other words, are all colorings connected by a series of Kempe loops? So can you go from one state, one arbitrary state, to another arbitrary state through a series of Kempe loops? And the answer is not always. So here's a visualization of the connectivity of the Hilbert space, where every vertex of this graph represents a coloring state. So for example, the Q equals to 0 state is here, and root 3 by root 3 state is here. And you see that there are two connected components. By the way, I need to explain what the lines mean. Okay, so the lines mean that if I have a Kempe loop that connects two colorings, then I draw a line between two vertices. So those are the edges, and the colors of the edges represent the length of the loop, because they come in different colors. For example, the loops of length 6 is represented as this pink thick lines, and so on. So you immediately see that even if I allow all Kempe loops of all lengths for this specific lattice, with finite size lattice, the states break up into two components. And of course, and the answer also depends on the periodic boundary condition, like what the periodic boundary condition is and so on. But at least in this case, it's not. There's no way to go from here to here. And because the loops have different lengths, now this naturally introduces some hierarchy in the component structure. So if you allow loops of only length 6, then some of the states are connected, whereas these states remain isolated. And as you're allowing longer and longer loop lengths, now more and more states get connected, and you have this hierarchy of connectivity. All right, so that's for 36 site with 168 colorings. I've done something similar for 81 site with about 45,000 colorings. If I allow loops of length 6 only, then you see that the states, essentially, the Hilbert space essentially fragments into little pieces. So these are all disconnected fragments. Yes.
Is there any, I don't know, topological numbers that label the various fragments?
Right. So the short answer is I don't know the answer. Because if it was something topological, then you would expect some finite number of topological invariants, right? But in this case, you have, I'll show you later, but you have exponentially large number of sectors. So I don't know what the answer would be. Yes.
I think it's maybe better if you move.
Maybe. Yeah, it's a follow-up to Darius' question. So, but if you look at the states in the different clusters, well, were you able to identify what's the difference? Because that would be basically, well, hint at the invariance. What is the sort of common feature of colorings in different clusters?
That's actually a good question. I tried to look at like if there's a way to classify some of the states. I mean, it's obvious that connected states have, let's say if you have a coloring state, it can have long loops and some short loops and so on, right? So if I'm allowing loops of length 6, then it means that that state is connected to another coloring at loop length 6, right? It contains Kempe loops of length 6. So that's as far as I got. It would be nice if there's something like a topological invariant that can.
Sorry, that's basically follow-up. I mean, I wonder basically here it's particularly simple because I think loop 6 is the minimal one that you can have. So I wonder if again, one way is to see what are the quantities that are not changed if you apply this loop updates. So I guess if you identify that, then you can try and see how the states in different clusters are different. So did you try that? I mean, I'm talking about perhaps some function of the coloring that is not changed by the loop update.
Right, some function of the coloring. It would be nice to find such a quantity, I would say.
I think I'll lose a kilo or two by the end of the talk. I guess graph theory people might know because I think they started the colorings.
I mean, it's not a question, neither a meaningful comment, but what you are doing somehow similar to discussions that I hear when people talk about topological data analysis, something like that, in which they start grouping points by some notion of length, and by increasing the notion of length, they start to have bigger and bigger groups. That you remember we attended in the retreat, we attended the talk about topological data analysis, and what you are doing looks really similar. So I mean, I know nothing about that, so maybe I'm just bullshitting, but I mean, it looks quite similar. So yeah, okay. But I know nothing about that. I can just tell you the slogan, but.
I mean, because Dario doesn't remember, you might want to check that that's the paper by Daniel Lycum. So you might want to check that.
Right, thank you very much for that comment. Right, so this is for loops of length 6 only. And I'm introducing longer loops now. If I allow loops of length 6 and 10, now more states are connected. And then as I go to longer and longer loops, 15, 20, and so on, now you have bigger and bigger clusters of states. So different states have very different connectivity, as you can see here. For example, the root 3 state belongs here in this tightly bound community in the center. And Q equals to 0 state is only connected to other states at longer loops because all of the loops are topological. And you can ask the question, how does the number of fragments scale with system size? And of course, it depends on the length of the loop. But let's say we do the simplest thing where we allow the shortest loop possible, which is the length 6, so only local loops. And I looked at systems with different sizes. I looked at all possible boundary conditions between 60 sites and 108 sites. And there's some subtlety in the fitting, but it does seem like it scales exponentially with the system size, with this number which is slightly smaller compared to the number of columns. So as you're going to larger and larger system, you have exponentially large number of colorings. You also have exponentially large number of components. And the average, roughly the average size of the components also grows, but it doesn't tell us whether all the components grow or there's some large community that grows really quickly. But at least that's what I find numerically. And this has some consequence. This fragmentation has some consequence in the dynamics. So if you prepare the system in some coloring, and then you let it evolve with time. And here I'm plotting what is often called the Loschmidt echo, which is the overlap of the original initial state with the time evolved state. And you see that the Q equal to 0 state does not time evolve at all because all of its loops are longer than 6. So there's no tunneling to other states at all. Whereas for the root 3 state, all of its loops are 6. So there are many, many decay channels. It decays the fastest. And there are states in between. And you have a broad distribution of timescales in this. And remember that this Kempe.
Sorry,
yes.
Can I ask something? Are there recurrences in finite systems here?
What do you mean by recurrences?
I mean, does it go log-Schmidt echo back to 1 for the square root?
No, I did not observe that. I don't think that happens here. I mean, if you wait long enough time, sure. Let's see. Oh yes, right. So different colorings belong to different size clusters, right? If the size is small enough, then you have a chance to observe a recurrence. In those cases, for example, the root 3 or root 3 state, you would have to wait like really long to really see revival.
Okay, thank you.
Right, so this Kempe dynamics and 3-coloring manifold was motivated by this XXZ Hamiltonian. So let's go back to the unprojected original Hamiltonian XXZ. At the mother point, at the JZ equals to -½ point, these coloring states are exact eigenstates, so they will not time evolve. So in order to give them some dynamics, you want to move slightly away from the exactly solvable point. And if you do that, again, you look at the log-Schmidt echo, you see some you see this discrepancy between the 2 equal to 0 state and the 3 state. So somehow some aspect of this dynamics is captured by this recording.
So I see that you have 81 sites modeled by full diagonalization. So I wonder about dimensionality of the system, because 81 seems a huge number to model on a computer. So
if you have spin half degrees of freedom on 81 sites, that will be impossible. But remember, I had this many colorings, so I can still do numerics within the coloring manifold. So if I just consider the coloring states as my basis states, then the Hamiltonian is small enough that I can do dynamics. Right. No, I mean this as a truncation from like the unprojected original Hamiltonian in some way. I mean, there's some, of course, there's a lot of subtlety. Like,
so this is the fragmented part of the whole Hilbert space, or?
That should be exact. You're just sitting in the manifold, and you only want to explore the manifold. That's very helpful.
Okay, yeah. So if I'm limiting to the coloring manifold, then I can study 81 sets. For the unprojected model, I can only go so large. So for example, this is for 18 sites.
So I mean, when you were looking at the XXZ dynamics, so what was exactly the perturbation? You went, you just changed the relation between JPerp and JZ.
Sorry, we cannot hear the answer.
Right. So the perturbation was I had the value of JZ to be slightly different from the -½ So different values of delta JZ here.
So what does it translate to in terms of the Kempe dynamics? So I mean, once you deviate away, I guess it couples to, you basically get an effective Hamiltonian with not just K6, but a whole distribution. So did you look how it looked like, this distribution?
Right, so you can, so let me try to answer that question. That's a good question. In spirit, you can think of this perturbatively, right? You at the JZ equals to -½ point, all of them are degenerate. Now you add in perturbation, you would typically, right. So that would be ideal. The subtlety is that this Hamiltonian is gapless. So you can't really do control perturbation series. That's one of the issues here. Yeah, right.
But then, I mean, what about going the other way? You explicitly want to add just K6. Would it be very unphysical for the XXZ Hamiltonian if you really try to enforce strictly like loop 6 dynamics? I mean, if you really want to enforce loop 6 dynamics, so in terms of the spins, would the operator be completely unphysical? Or, I mean, did you consider that?
Yeah, that's also a good question. I need to think about that. Because you need a way to introduce some cutoff in the two-body Hamiltonian, right? So
the reason I'm asking, I think people did again something similar for, I'm not sure if it was Kagome or Pyrochlor, but I think they added the induced dynamics in the spinized manifold that way, and I think the operator was more or less reasonable.
And there, I think, if I remember correctly, there you have like a well-separated manifold, right? You have a well-defined gap. Yeah. So in that case, you can control stuff, but here it's tricky.
There's actually the question I asked to Arjit Pal. He was talking on Monday. So I think you know the work of Owen Benton. So he generalized this model. He basically showed that you can have a family of models which share these properties. Essentially the same, well, yeah, I don't remember exactly. The model looks very similar. So you can so you have a family of models sharing same properties as this one. I don't remember though whether they're all gapless or gapped. So I wonder, did you, well, Arjit seemed to be aware of this work. So I'm curious, did you check whether some of these models are gapped so that you perhaps could exploit that?
I don't remember on top of my head. I should revisit this. Okay, so there was a number of proposals for realizing this in experiment. For example, using P plus IP Josephson junction arrays if we ever find a P-wave superconductor, or using S-wave Josephson junction arrays but with very strong magnetic field. And recently there's been a lot of progress in realizing model Hamiltonian using Rydberg atom arrays. So I think this is one of the promising avenues. And one thing that I want to point out is that this the similarity between these two graphs. So even though, I mean, these are both graphs, right? So the positions of the vertices don't really have a meaning, but it's only the connectivity that matters. But I've used some algorithm that prefers like introduce attractive interaction between states that are connected by shorter loops. So I used the same algorithm to produce these layouts, and then somehow they ended up with like very similar looking graphs, even though the number of colorings is very, very different. For example, there's this strong and tightly bound community in both cases, which is expected from short loops. But then there are these three things protruding out, and also the component B has this binary structure. So there's some similarity that I noticed. I don't know, but it would be nice to have some analysis or some understanding of this. But unfortunately, I'm not an expert on that, so it would be nice. Yes.
Probably I'm missing. I may be missing something, but does it also contain the real space information in this graph?
What do you mean by this?
I mean the distance, for example, distance between the loop or displacement, the relative displacement between the two loops, or yeah, some other real space information.
I would say the only real space information that this contains is first of all that these basis states are local product states. So that's one thing. The other thing is that there's a length scale associated with the loops. So I think those two are the only information that's in there. If you're asking whether the real space, somehow the real space structure is determining where the vertices go, then that's not true. Okay, so am I almost out of time or?
We have still 10, 15 minutes, 15 minutes. There was lots of discussion, so.
Okay. Right, so as I promised, this is slightly different from what I've been talking. Now we talk about coloring manifold and how it's how the submanifold defined by that three coloring is fractured into little pieces. Now me and my colleagues have found a way to also engineer quantum scars in these three coloring models. So and make a little change in the Hamiltonian. So as I said, yes.
Okay, well, I mean, it's a quick question. So the original model doesn't have scars.
Right, so it's a slightly different model. Again, the Hamiltonian could be written, the XXZ Hamiltonian could be written as the sum of triangles. Now, if you flip the sign of the interactions on some of the triangles, it's still a two-body interaction. And all of the arguments on why the three coloring states or eigenstates still apply. But the difference is that now the three coloring states are no longer in the grounds, in the lower energy manifold. Now they're in the middle of the spectrum because the up triangles and down triangles cancel. So these are essentially infinite temperature states, which are also product states and eigenstates. And that fits the definition of quantum manifold scars. And if you look at the entanglement of these coloring states, these are product states, so there's no entanglement. But if you do, now let's say, because SZ is a good quantum number, you can do projection to a particular SZ sector, and that introduces some entanglement through conservation of the quantum numbers, but it scales as log of V. So you have a subvolume law entanglement in this case. Now you can apply magnetic field to the outer plane magnetic field to the system. The coloring states start precessing, and you see a perfect revival. Oh, it's not moving. Okay, yeah, these spins are supposed to rotate, but somehow.
Are the perfect revival, let's say, really perfect in the sense analytically you can see that they are equally spaced in energy or not, or it's just approximate?
Right, so if you consider a single coloring state, right? Now you can split that into different SZ sectors. And then you apply outer plane magnetic field, different sectors acquire, I mean, you see that it's equally spaced, right? Depends on the total SZ of the Hamiltonian. So you have macroscopic number of spins that are rotating, like precessing coherently. And this revival seems to be robust against perturbation. So if I go to a point slightly away from JZ, you still see, it's not perfect revival, but you do see some saturation. This envelope seems to saturate to some value. Now, the question is then, does this survive in the thermodynamic limit? And I would love to know the answer, but at least it suffers greatly from finite size effects. So. But at least, at the JZ equals to minus half point, we can analytically prove that this is the case. I've looked at a slightly different model where frustration gives rise to some submanifold with some local constraint. But this ends up being a very different scenario. I'll just quickly go over it. Again, I can look at the connectivity structure of that submanifold of the perturbative Hamiltonian, and you see this three components. You don't have exponentially large number of components in this case. I think the situation is similar in the quantum diamond model and probably also in like spin ice case. If you look at a larger system, again, you only have 4 components, which are perfectly understood in terms of topological sectors. So these different components correspond to different topological sectors. And that's why you don't have any connection between different components. And what's also interesting is that there are these 16 isolated states that are not connected to any other states. And these are what I call the pinwheel order states, which have this kind of shape, where the black dots represent upspin and the white dots represent downspin. And this somehow does not, it vanishes upon the perturbative Hamiltonian. And so this product state, which is an eigenstate, sort of fits the description of quantum many-body scars, although it's a little more shaky in this case. It's in the, right, so let me explain. So this Hamiltonian has fully connected hexagons and in the Ising limit. Right? So that defines a submanifold through a 3 up, 3 down constraint, which is like, it's very similar to ice roll. And this state also lives in that manifold. Okay. Okay, let me skip the level statistics and finish with the summaries. So talked about how frustration can give rise to some submanifold of the Hilbert space with local constraint, which can give rise to fragmented Hilbert space and showing athermal behaviors. And this contains very rich dynamics, including like Glassy dynamics and quantum scars, and some of the open. Let me just, leave the open questions there and take any questions if you have any. Thank you.
Okay, thanks, Dr. Kyungmin Lee, for very interesting talk. We also had many questions, but we also have this time for questions. So anyone, Dr. Chang-Wan Lee?
The original definition of scars is a kind of a wave localization of the periodic orbit in chaotic systems. Then how can we make a link between your quantum scars of many-body and then the original definition?
Right. So, the study of quantum scars and many-body systems has been motivated by this, largely motivated by this experiment in like Rydberg atom arrays, where they saw very slow relaxation dynamics in some of the configurations. And the authors of that work have coined the states quantum many-body scars. So these are very slow decaying or not decaying at all, right? So in terms of the eigenstates, right, you can think about these scars as eigenstates which are weakly entangled. So in general, if you have eigenstates at finite energy density, you should follow volume law according to ETH. But if for some reason in some models, if you have eigenstates that have subvolume law entanglement, like extreme case would be product states which are eigenstates, or area law entangled eigenstates, then these are, that's one of the defining qualities of quantum many-body scars. So these are measure zero states that are behaving in a very different way compared to other eigenstates.
I have more of a comment, not exactly related to your main topic, but you mentioned that there is some well-known entropy difference between when you take the definition of entanglement entropy. You know what I'm talking about? There was a graph you said this is a well-known difference in entropy. Yeah, so I believe that this difference comes actually from using the wrong definition of entropy. Because if you take entanglement entropy, basically if you cut the system in half, the entanglement entropy will be approximately proportional to half of the thermodynamic entropy of the full system. So when you multiply by 2, basically what you are doing, you are summing two entanglement entropies. But entanglement entropy itself has the information content of the system plus the mutual information. If you multiply this by 2, you will account for the mutual information twice. So if you subtract mutual information, which is, by the way, for example, for systems, when you have conservation law, like an energy conservation law, this overcounts the entropy because it doesn't take into account that there is some dependence of between energy of one system and the other system. So that's why you overcount the entropy. If you subtract this mutual information, you will get something that's lower than the total entropy and almost exactly the same. The alternative way is to use different definition of entropy, which is, for example, coarse grain entropy or observational entropy with local energy coarse gaining, and then you don't get into this problem at all.
Thanks for that comment.
Do we have any further questions from the audience?
Two or perhaps one question. So you mentioned the implications on spin liquid physics, and you were also mentioning Glassy dynamics. So did you, did you check the ground state once you allow the different colorings to talk to each other? What kind of ground state do you get, a glass or a spin liquid?
Right. So that's also a good question. So when I was discussing this dynamics of the states, right? So you're talking about here, and I did not do a further analysis. I mean, I would love to do it and figure out whether the ground state is and so on. And one thing that I can say for sure is that there's always some states that if you introduce some loops with finite cutoff, there's always states that have longer loops only. So there are always states that do not decay. That's one thing that I can say for sure. And that will appear not just in like Boschmidt echo, but also in like some observables. If you measure spins for long enough time, it will not change and so on.
Are there any, so far you were focusing on the coloring models. So are there any other known examples? Other classes of models, perhaps where similar phenomenology would emerge? I'm perhaps thinking of 2D quantum models with discrete and highly degenerate ground state manifold. So do you know of any examples and that are not based on 3-colored?
So I know there are some models in 1 dimensions that people talk about, like this submanifold and fragmentation there. Right. But you can sort of justify those in like perturbatively, right? So yeah, I don't know any other models in 2D.
If there's discussion going back and forth, the people on Zoom cannot hear it. So please keep this in mind.
Do you have any other questions from online, or then we had a lot of discussion also. I again thank Kyungmin Lee, Dr. Kyungmin Lee for coming, and we may have an informal discussion maybe, so let's end the talk at this moment. Thank you.